I'm representing Avi today. As happens every now and then, Avi has to travel on Thursday. And we actually have a very interesting lineup this morning. We start out with our own Diamond-Lowe. She's up there ready to go. And then the colloquium speaker for later this afternoon, Sarah Hörst from Johns Hopkins, will speak briefly. And then Stella Offner, who used to be here, who's presently at UT Austin, will come up, and then again another of our own, Theron Carmichael, will speak. I'll give the titles as we move forward. Also, I think I neglected to mention, Stella did just give the ITC colloquium, so she barely had time to catch her breath and relax into it. So with that, I'll hand the floor to Hannah Diamond-Lowe, who's going to talk on ground-based transmission spectroscopy of nearby terrestrial exoplanets.
Thanks, okay, yeah. So ground-based transmission spectroscopy of nearby terrestrial exoplanets. We should probably first define what a terrestrial exoplanet is. So this is work by B.J. Fulton et al. That came out a couple of years ago. And using 4 years of data from the Kepler mission and some follow-up with the California Kepler survey, they're able to make this histogram. So we have number of planets on the y-axis as a function of planet size and Earth radii. And what emerged from this work is that for small planets, those with radii less than about 10 Earth radii, there appears to be this bimodal distribution of planets with a valley at around 1.7 Earth radii. So a radius alone cannot tell you about a planet's composition, but when you combine a radius with a mass, you get a density, and a density can tell you something about the bulk composition of a planet. So now the planet radius is on the y-axis, planet mass is on the x, but I've shaded the regions accordingly. So in this blue shaded region is where we have planets whose radius and masses make them have a rocky composition. So this gray curve is the rocky composition curve. The blue dots are the solar system planets. So you can see Earth and Venus are right here on the rocky composition curve. And so we do actually have a small sample of planets for which we can determine that they are terrestrial based on their radius, radii, and masses. And so what can you ask beyond that? And for me, the next most interesting question is, what do their atmospheres look like? So to address this question, we can use the technique of transmission spectroscopy, which I'll just walk through really quickly so everyone is on the same page for what it is. So the sort of governing equations that we need to make a transmission spectrum for an exoplanet are the transit depth. So this is just the radius of the planet as a ratio of the radius of the star squared. And if you want to understand its atmosphere, you also need to know its atmospheric scale height. So this is usually termed as H, and most of the values in the atmospheric scale height are either constants or are derived directly from the planetary parameters. The true unknown that we want to figure out is this mu, this mean molecular weight, and this depends solely on the composition of the planet's atmosphere. If you have a small mu, so a hydrogen or helium-dominated atmosphere has a mu of about 2. That gives you a very extended, puffy atmosphere on top of your planet. If you have a larger mu, your atmosphere is held more tightly to the planet's surface. So just a quick illustration of how this works. Say in this example, this planet has a lot of water in the gaseous phase in its atmosphere. If you observe the transit depth of this planet at one wavelength, where water is transparent, you would measure a certain transit depth for this planet. If you looked at this planet transit at a wavelength where water is absorbing, you would see a bigger transit depth, and the planet would appear larger. So to apply this technique, we want to figure out what are the best terrestrial planets to do this for, and luckily Eliza Kempton came up with the transmission spectroscopy metric, which takes into account the planet's mass and radius and the stellar radius and how far away the star is and all the sort of ingredients you need to say, like, well, will this planet have atmospheric features that we might be able to observe in transmission? And the planets that I'm most interested in are these terrestrial exoplanets. So these planets with about radii less than 1.7 Earth radii. And the ones that we can really hope to observe with the transmission spectroscopy method are ones that are nearby, within 15 parsecs, and orbit small host stars, so less than about 0.3 solar radii, or M-dwarfs. So I have, in the last 4 years, focused on a few examples, which I have here in red stars. And I've used the Magellan telescopes, which the CFA is a partner in, to observe many transits of these planets up here. You could ask me why we went after 1140b later, if you want to. So I do want to thank Scott Kenyon and Warren Brown for all their effort in scheduling these transits. It is not easy to schedule a transit when a lot of other people just want to look at galaxies, and you want to be like, no, I need 5 hours in the middle of the night to observe a transit. So these were all the transits that I was awarded. These were what we were actually able to observe when the weather permitted. And so this sort of is how we built up our sample set. I'm going to focus on the results, the most recent results from LHS 3844b, for which I was awarded 20 transits, 13 of which ended up being observed. So this is what 13 transits looks like if you don't do any detrending. All the different points represent each of the 13 transits. The gray is the model. And the point of doing this 13 times is that we can jointly fit all 13 transits together to make a measurement of the transit depth that is robust. And so that's what this looks like. So here all 13 transits were fit together, and now we have a really good measurement of the transit depth, which, if you recall, is this ratio here. Now, the transmission spectrum, you need to do this for a lot of different wavelengths. So if we take this transit depth and bin it up into different wavelength bins, you end up getting a whole bunch of wavelength bins with all your different transit depths. So they can't all fit on the page, but if you just focus on your favorite one, so this is a 20 nanometer wavelength bin, and this is what the transit depth looks like when you stack all 13 transits together in that wavelength bin. And now we're going to plot these transit depths as a function of their wavelength bins to get the transmission spectrum. So here we have the transit depth on the y-axis as a function of the wavelength bin. If you just focus on the orange data points for a moment, these are the transit depths that you get from fitting all 13 transits together. And the error bars are the 1 sigma error bars. To guide your eye, I've put up a model spectrum of what this transmission spectrum should look like if this planet had a puffy hydrogen and helium atmosphere around it. As you can see, so that's recalled back from this mu factor. This model has a mu of about 2.36. And as you can see, our data do not fit this model, suggesting that this planet does not have this type of extended atmosphere. And I just want to illustrate quickly why we did 13 transits. So I'm just going to show the transmission spectrum here from one transit, and then I'm going to add another transit, and a third and a fourth, and so on. Is that going to work? No. Try again. There we go. So if you look down here, this is how many transits are going into this transmission spectrum. And as you can see, the error bars are shrinking, and eventually we settle on this transmission spectrum that we get at the end, in which we're able to rule out a low mean molecular weight atmosphere. So I've done this for a couple of systems. Others have done it for some of the TRAPPIST planets. And what seems to be the trend is that low mean molecular weight atmospheres are disfavored for terrestrial exoplanets. So all the red X's up here show which planets we have, to high confidence, ruled out these sort of extended hydrogen and helium atmospheres. So that's basically it. I just want the sort of main takeaways. If you didn't listen to anything else, the terrestrial exoplanets whose atmospheres we can observe with the instrumentation available to us in the next 10 years are those that are nearby, less than about 15 parsecs, and orbiting small stars, or M-dwarfs. And it seems now unlikely that these terrestrial planets have low mean molecular weight atmospheres, which I would just say is kind of exciting because it means we can think of these terrestrial exoplanets as having atmospheres that are similar to the solar system terrestrial planets, maybe not necessarily in terms of composition, but in terms of having high mean molecular weight atmospheres that are packed tighter to the planet's surfaces. Thanks.
Two questions. One, how many stars, terrestrial exoplanets, will you be able to observe in the next 10 years? Or you don't know which of these stars that are nearer than 15 parsecs have planets?
Yeah, so this plot is still being filled out. The TESS mission has added a number of these planets within the last year. And so we're hoping that we can find a few more that are amenable to atmospheric follow-up. But from what we know about planet occurrence rates and transit probabilities, we're not going to add on order 100 more. We might add on order 5 to 10 more.
And the second
Yeah.
question is, could you go to your first slide? Please?
Yeah.
First slide.
Yep, we're going. This one?
Whoop. No, I'm sorry.
Okay, this one.
What is the light gray
This?
with less than 1 Earth?
This is just showing that the sample is not complete out there. It's very hard to observe a planet with less than 1 Earth radii. So it's just showing that it's not a complete sample there.
And you just made it that shape just arbitrarily.
Well, this is from B.J. Fulton et al. This is what they get, but the error bars are so large that it's not sort of, they didn't want to draw attention to it on the figure.
You walked the error bars and made it correct.
I believe that's what happened. Yeah, I'm going to do it this way because it took too long last time. This one?
Yeah.
Okay.
It does seem like it's declining somewhat to the red.
Yeah.
Is that significant that it's
Yeah, it seems significant in that actually a flat line also doesn't well describe these data, but we don't know why. If anyone's thinking it, it's not Rayleigh scattering. We're too far in the red part of the optical for that to be the case. But yeah, we're thinking about that. It is kind of interesting though. Yeah, good eye.
To rule out, this was very nice, right? Now you've ruled out this hydrogen and helium atmosphere. If you looked at it from the theoretical side and said, well, hydrogen and helium are going to typically be the first to evaporate and
Right.
be lost. So can you combine your observations with theoretical computations of how long you would expect these atmospheres to survive and whether, given the potential ages of these systems, you might actually be able to predict further results?
Yeah, no, that's a great question, and definitely we do this. So there's, especially for these terrestrial planets around M dwarfs, it's really important to know the UV profiles of these M dwarf stars. M dwarfs exist much longer in the pre-main sequence phase than solar-type stars, and they show higher levels of activity for a longer time. So this was not a terribly surprising result, I will say. The theory does say that over time, if there were an atmosphere like this, it would definitely be lost through either genes escape or from photodissociation of, say, water molecules, and then you have the hydrogen escaping, and then it can drag along heavier elements with it. So people are definitely putting together these ideas, and this is sort of an empirical observational check. This planet in particular, we don't think has an atmosphere at all, and that was some recent work from Laura Kreidberg, who used Spitzer phase curves to determine that. So this was sort of moving into the optical, just sort of seeing what we see. Yeah.
I was wondering how the transmission spectrum varies night to night if you have the precision to tell whether it's varying and whether or not that's related to stellar activity and whether stellar activity
Yeah, so
downward slope.
yeah, the downward slope seems fairly stable, which is interesting. But if in the movie, I won't show it again, but there was some sort of jittering around until it kind of settled on the final spectrum. I will say that sort of overall, moving the spectrum up or down is not really important. we're not measuring an absolute transit depth at any of these wavelengths. It's all about the relative transit depths. That's what we really care about. The night-to-night variations, there is something that could come from stellar activity, although this is not a very active star. It has a very long rotation period. I'd say more likely it comes from the ground-based observations and the Earth night varying in terms of like wind, precipitable water vapor, things like that. Yeah. It's been...
Too many logistics.
Do you need help? I'm getting this.
This is maybe Ninja Turtle. Is it still on? Is it still on? I don't know. Did you mute it?
No, I think they do it for that.
Ah, that's sneaky. Okay, let's see if I can actually do something like this. Okay. Ooh. Are you working? Wait, no, don't go. Stop. Hi. So later on, I'm going to talk about experiments and atmospheres and everything. But actually, I think the most exciting thing that certainly happened to me in the last 6 months or 3.5 years, depending on how you do the math, is Dragonfly. So I thought I would take this smaller opportunity just to talk about Dragonfly, and this is going to be literally my only slide. I thought about going no slides, but sometimes that ends badly. So I actually just want to talk to you a little bit about the mission concept. So, and to emphasize, I guess at the beginning, that we are now selected and moving into phase B. So this is a mission that presumably will fly, barring all of the bad things that happen between phase B and arriving at your destination. And so Dragonfly is a dual quadcopter that we are going to send to Titan. Titan's the largest moon of Saturn. It has 1/7 the gravity of Earth, and it has an atmospheric density at the surface that is 4 times that of Earth. And so it is the very best place in the solar system to fly. And so that is what we are going to be doing. So just to give you a sense of why we're so interested in going back to Titan, we now know from the wildly successful Cassini-Huygens mission, which ended 2 years ago, that Titan has the most complex organic chemistry in the solar system, besides the chemistry that is occurring on Earth due to life. And so we believe that Titan is one of the most important places in the solar system to try to understand the chemistry that might lead to the origin of life, that may have led to the origin of life on Earth, and also is potentially habitable or inhabited now. And so the questions that we really want to answer by going there involve doing a really detailed study of the chemistry. And so that is what we had proposed to do. One of the challenges that we have on Titan is because we have this thick atmosphere that's covered in this substantial organic haze, which is what I'll be talking about this afternoon, it's very challenging to study Titan from orbit. We have done it. We did it with Cassini. And we learned a lot about the atmosphere. We learned that the surface is very diverse. Titan is a very Earth-like moon. We have rivers and streams of methane and ethane. We have mountains. We have extensive organic dune fields. And so there's all of these different environments that we would really like to learn about. If we were Mars, the way that you would propose potentially to do that is to do that with a rover. But designing rovers that function at 94 Kelvin on a surface that you have no idea what it's made out of is a little bit challenging. So we thought the easy solution to the problem would be to propose the first flying spacecraft that NASA has ever sent. NASA seemed to agree with us, which we're still a little bit perplexed about, but we're not going to say no to their yes. And so this is what we propose to do. So I'll show you this animation quickly just to give you a sense of what we've apparently gotten ourselves into. So by the way, we launch in 2026 and we get there in 2034. So we're already eating our vegetables and doing a lot of yoga and cutting all the vices out of our lives. But after that very, very long time in which, you know, nothing particularly exciting happens, this is what's going to happen the day that we get to Titan. So we descend on parachute. We have no orbital element, and so this is us. We figure we might as well make the beginning exciting, and so we actually have to fly off of parachute. So we lose our parachute about 1 kilometer above the surface. We'll fly to our initial landing site, which is somewhere called Selk Crater, which I'll talk more about in a second. This is what the lander looks like, at least our concept right now. We're powered by an RTG, which is the kind of cylindrical feature on the far end of the spacecraft. That's our high-gain antenna that just deployed, so we have to do direct-to-Earth communication. On the 2 skids in the front, you can see that we're carrying 2 drills. And so we'll actually be drilling into the surface to sample material. And so we're carrying a suite of instruments that are really designed to answer questions related to what I just mentioned we find so interesting about Titan. We have a gamma-ray neutron spectrometer that's going to basically tell us about the bulk composition under us wherever we land. And our intention is to take off and land hopefully many dozens of times. Our nominal mission is 2.5 years, and in that period of time, we think we will probably fly on the order of about 20 times. But we can go into extended mission as long as NASA will let us, and so we should fly many, many times. So we'll get bulk composition information from the gamma-ray neutron spectrometer. We have a meteorological package, which will do temperature, wind speeds, methane relative humidity, which will help us figure out whether or not it might rain tomorrow, and so maybe we don't want to fly. We have a seismometer. Our kind of main instrument that is designed to answer the science questions that are really driving this mission is a mass spectrometer that's being built by NASA Goddard. It will be the most capable mass spectrometer that has ever flown in space. And with that instrument, we'll be able to search for things like amino acids, which are the building blocks of proteins, nucleobases, which are the building blocks of DNA and RNA. These are things that we actually very much expect to be there based on everything that we know about the chemistry. And so we really want to figure out how far that chemistry has proceeded on Titan. This is important for 2 reasons. One reason is because we really need to know how far that chemistry proceeds abiotically, so that we understand what the building blocks are for life. That, you know, we can kind of assume will be anywhere where there has been complex chemistry. You know, if it's super, super simple, that means life has to do a lot of work. If you can get pretty complex without life, then that makes the origin of life easier. But the other reason is that we really need to understand this complexity of abiotic chemistry so that we can search for life. So if we're looking at the atmospheres of these planets that Hannah just talked about with James Webb, and we see different molecules in the atmosphere, how do we know if that's the signature of life or not? And so that's one of the reasons why we're so interested in studying this complex chemistry. Maybe Titan has life, maybe it doesn't. We're going to go a long way to answering that question with Dragonfly. But even if it doesn't, we're going to really learn a ton about how far complex organic chemistry can proceed. And so to do that, we have basically already chosen our landing site, which makes us very different than a lot of Mars missions, which spend like years yelling at each other about where they're going to go. We didn't have like a whole lot of options because we had one very specific criteria in mind. So Titan's surface is made out of water ice, right? It's 94 Kelvin. At that temperature, water is like granite. But whenever there's an impact into the surface, you get a melt pool that can last for tens of thousands of years. And the chemistry that occurs at the interface of this really complicated organic chemistry in the atmosphere and interactions with liquid water is super interesting. And so we want to go to places where we are sure that that has happened on the surface to see how much further the chemistry proceeded with the presence of water. That's important both for thinking about whether or not Titan is habitable or could be inhabited, but it's also important because we know that Earth has liquid water and has had liquid water for a long time. And so if we want to think about the processes that happened on the early Earth, we want to include the chemistry that was happening with liquid water. So to do that, we're going to a crater called Selk Crater. So it turns out that craters are pretty rare on Titan because there are all of these active processes happening on the surface. We've confirmed the presence of about 10 craters on the surface, which for those of you who know anything about how many craters planets tend to have, that's not very many. We also have about 50 what we call suspiciously circular features, for which we have no topography, and so we can't actually tell if it's a crater or not. But there aren't that many planetary processes that make craters that make round features. course, and so presumably those are also craters. But given that we only had 10 for sure, that eliminated a lot of potential landing sites. Selk is one of the larger of those craters, and it also happens to be on the part of Titan that we can access when we get there, so that's important. You should be able to actually get to your landing site if you want to land there. We'll be landing south of Selk crater in an area that has a pretty substantial dune field. And we'll be landing in the inner dune region. The main reason for that is that should be a very safe landing site. If you've ever spent any time in dune fields on Earth, the interdune regions tend to be a very flat. They tend to be effectively very uniform particle size, and so you don't have to worry about there being boulders of all different sizes and stuff like that. Oh, that reminds me, I forgot to mention one thing. Everyone gets this vision of like your toy drone that you play with in your backyard. Dragonfly will stand about this tall on me, so it's like 4.5 feet tall, and it's 10 feet long. So little rocks are not going to cause us problems, but we would not want to land in a boulder field, at least not on our first landing attempt on Titan. And so we're going to the interdunes region, both because we're very interested in measuring that material. We know from Cassini that it is organic. We know those organics were made in the atmosphere, and so it's very possible that a lot of the molecules we're interested in will be present at that first landing site. But we're also going there because we don't want to end the mission on our first landing attempt. We'll have plenty of other tries later in the mission to end catastrophically during landing, but we would like to not do it on the first try. I mean, we would like to not do it at all, but the first time we should at least land somewhere safe. And then we'll eventually make our way to Selk crater, then into Selk, and hopefully actually fly all the way eventually across the crater and back out again, and then we can continue on to explore other regions of Titan. To preempt a question that I always get asked, everyone wants to know why we're not going to the lakes, or if we're going to go to the lakes. All of the existing lakes at this period in Titan's history are at the North Pole. When we arrive at Titan, you cannot see the North Pole from Earth. And because we're doing direct-to-Earth communication, seeing Earth is actually a requirement. And so we cannot go to the North Pole at the beginning of the mission. We could make the choice to fly in that direction, but we probably will not explore any of the permanent liquid environments on Titan. But we may have the opportunity to explore places where it rains and to see what those interactions are like. I think that was all I was going to say. But I would love to take questions. Yes. Yeah. We really don't like to think about this part. Don't tell NASA I said that. So the one-way light time to Titan is about an hour, depending on where exactly we are in Saturn's orbit. So everything is fully autonomous. That means that, and so we don't have a GPS satellite network. We also do not have good maps of Titan because we haven't been able to see the surface very much from space. So we're going to be taking a lot of pictures, and it's going to be real smart, is the plan. The one thing that we will be doing, so our first landing, I think, at least for me, is going to be the scariest, not just because that's going to be the first time that we demonstrate that we fly, but that's also going to be the time that we are landing with the least information. So after that, every time we fly, about half of our flight is going to be getting to where we want to go, and the other half of the flight is going to be scouting for the next flight. And so we're always going to overshoot where we want to land to do a bunch of imaging of the area in the direction that we think we're going, and then we'll fly back to our landing site. So after the first landing, the decision-making in terms of where to go and how to get there is going to be a combination of us having made the decision based on the data that we got, and basically telling it okay, we want you to go there, but it is also going to have a lot of capabilities to, as it's landing, be and scoot over here. And then also, of course, it has to be able to have decision-making capabilities if something happens during flight. So if there's some kind of mechanical issue, it has to decide, is this urgent enough that I just go down now and hope for the best? Do I have 5 minutes to, pick the best option within a 5-minute flight of here? And it's going to have to do all of that autonomously. Yeah, that's fine.
question, do you run out of power? And the second question is, are there things like winds and storms you would worry about?
Yeah, so I'll do the second question first. So one of the other reasons why Titan is a really good place to fly is because at least in the deep atmosphere, the wind speeds are quite low. There are storms on Titan. It does rain, but they happen very infrequently. And actually, the time of Titan's year that we are going, oh, and I forgot to mention, Selk is equatorial. So we're going to the equator at a time of year where we've actually really never seen a storm on Titan. And so the expectation is that we probably won't have to encounter particularly high wind speeds, particularly vigorous storms. But of course, we have to be prepared for that. But we're certainly not going to be trying to fly in like hurricane force winds ever. That's not something that we have to worry about so much. I forgot your first question. Oh, what sets the length of the mission? So for the most part, like cost cap sets the length that we could propose. So like I said, we're powered by an RTG that charges a battery. And so the good news about that is that as our RTG decays, we can just sit for longer to finish fully charging the battery. Our power-intensive activities are flying, obviously, drilling, and also the mass spectrometer uses quite a bit of power. But we can just charge the battery longer as the RTG decays. Eventually, we won't be able to get enough power to fly, but we would be a great landed asset for doing meteorological monitoring, those types of things. The really rate-limiting thing, the time limit thing that will eventually kill us is eventually the RTG will decay sufficiently that we actually can't keep warm and we'll freeze to death. It's unclear if we'll actually, do science up until that point. But we should be able to have a pretty robust extended mission, assuming that everything works correctly and NASA wants to keep giving us money.
Wasn't Cassini deliberately plunged into Saturn to avoid inadvertently contaminating the moon, and now?
What are you trying to say? No. Well, so the good news is this actually isn't the first time we're going to be landing on Titan. So Titan already got ruined. So the main issue with Cassini is that, well, it is absolutely true that that was one of the main reasons why Cassini's mission ended that way. Cassini was never designed with the idea that it would impact a moon. And so it wasn't subject to the same planetary protection controls that something like Dragonfly would have. And so that was the reason for that, was basically it had never been cleaned to the point that we would have been okay with it crashing into Titan or Enceladus. Part of the reason for that was actually we didn't know about Enceladus. Well, I mean, we knew it existed, but we didn't know that it had a subsurface ocean. We didn't know that it is potentially a place that harbors life. And so I think that if we had known that, Cassini would have been subjected to much stricter planetary protection rules, but we didn't, and so it wasn't. And so then we had to be extra careful. Obviously, we have to be extremely careful with Dragonfly. Some of you may be familiar with the fact that NASA has recently been reevaluating its planetary protection guidelines and protocols and all of those things. So we don't actually have a lot of our guidance yet about what we're going to have to do. But the good news is that selfishly, we don't want to take any creatures with us, because if we see something, we want to be real sure that it's Titanian and not Earth. But yeah, it's something that we do have to be very, very careful about, and particularly because we have the RTG, which leaves the possibility that if something catastrophic happened, we would melt ourselves a nice little pool of water. That adds an extra level of planetary protection controls that we're subjected to. Yeah.
Okay, so let's acknowledge that was a really hard talk to follow. So this is probably not going to be as exciting as Titan, but I'll do my best. So I'm going to be talking about the impact of cosmic ray feedback on accretion and chemistry in circumstellar disks, which I think in some areas of research, does have influence on the origins of life. So why should you care about cosmic rays and star and planet formation? For a long time I didn't. I thought cosmic rays were super boring. But the longer I thought about this topic and really understood the chemistry of what's involved in star and planet formation, the more I understand how important cosmic rays are important. So cosmic rays cause ionization. So we're talking about high energy electrons and protons that are relativistic. And as they're traveling through the gas, they basically ionize the gas. And you can quantify this in a kind of ionization rate parameter zeta, so ionization rate per second. For reference, the galactic value of this is maybe 10 to the minus 16 ionizations per second, all right, with some variation. So star and planet formation. This ionization rate parameter is crucial for molecular cloud chemistry, including helping to determine abundances of CO, carbon, and ionized carbon. And cosmic ray heating impacts cloud temperature, so it also shapes cooling and heating processes. It turns out that the ionization of clouds and cores is important for non-ideal magnetic effects. So it could help regulate things like ambipolar diffusion and ultimately influence angular momentum transport and the rate of collapse. So it also, on much smaller scales in terms of protoplanetary disks, the ionization of the disk is really important for whether or not the magnetorotational instability is active. So anything to do with accretion or turbulence within the disk depends upon the local ionization. And we think planets are forming in the midplane of the disk where it's dense. But for that to happen, we need a very neutral gas, one that's not subject to the MRI. So we need a nice quiescent dead zone for planet formation to occur. And finally, these cosmic ray ionizations really spark a huge range of chemistry, leading to a lot of complexity that ultimately may be important for molecules that are relevant for life and habitability. So today I'm going to talk about this part of the diagram in DIS. So just so we're all on the same page, this is not a talk about cosmic rays from supernovae. Not about supernovae. Okay. So instead, it's actually a talk about cosmic rays that are produced during the star formation process itself. So I became interested in this a few years ago when Marco Panavani proposed that accretion shocks and jets from forming stars could accelerate cosmic rays. So this process is the same one that produces cosmic rays in supernova. So basically you have some long-lived shock with some magnetic fluctuations, and particles are accelerated as they bounce back and forth across your shock. So this was extremely surprising because it basically suggests that the cosmic rays could be coming from inside the house. All right, so not supernova, but they're produced locally, very close to where the action is happening in star formation. So I think this is a very exciting result. All right. So what's actually happening here? So what we did is we built upon Marco's work and calculated the spectrum of electron and proton cosmic rays that would be produced from these shocks. And one of the big takeaway points is these are low energy cosmic rays, very low energy cosmic rays. So if you work on supernova, you may not even pay attention to these. But it turns out they're very important for ionization. And again, these would be screened out of clouds of this energy. So having a local source inside the cloud could be really important. So what is the evidence? It turns out there is evidence that cosmic rays are being accelerated. We see observations of, in jets, we see non-thermal synchrotron emission, particularly associated with knots. And so this suggests that there are cosmic rays there which are creating this emission. We also see evidence associated with protostars. And my favorite example of this is OMC2 FIR4, which is a dense core that's forming a massive star, maybe 10 solar masses. And three different groups now, and a variety of different chemical tracers that probe the ionization rate, have inferred cosmic ray ionization rates above 10 to the minus 14 per second. So more than 2 orders of magnitude above the galactic value. So that is pretty extreme. If you go ahead and make a model for cosmic rays produced, say, during accretion, you can explain this ionization rate locally. Now, what about disks? So in this recent work, I wanted to know what impact cosmic rays produced locally from accretion shocks and jets might have on disks and disk chemistry. So this is an important application. A few years ago, Ilse Cleves noted that the magnetosphere of these young stars probably screens out cosmic rays from the local environment, just like our own sun's magnetosphere screens out low-energy cosmic rays from the solar system. So if this is true, then cosmic rays are not so important. But it would not apply to local cosmic rays. So there would, again, still be a source inside the house. So in this work, we wanted to take into account not only cosmic rays, but stellar, FUV, and X-rays. So we have all the sources of ionization, including long-lived radionuclides, to try and estimate within the disk what the ionization rates are and whether or not these cosmic rays would make an impact in terms of promoting the MRI and the onset of turbulence. So we calculate, starting from the accretion shock, cosmic rays attenuate, particularly low-energy cosmic rays. So they're interacting with the gas that's falling onto the star, right? So they can be attenuated that way. They can also diffuse outwards, and the spectrum decreases. So we follow the cosmic rays as they propagate to the disk surface. But even as they're dropping very rapidly, as they go outward, you still have very high ionization rates at the surface of the disk, which is potentially important. So if you don't consider cosmic rays, right, the normal ionization is provided by FUV and X-rays. X-rays penetrate very deeply, but not to the midplane. So cosmic rays have the unique property that they can reach extremely dense gas. And the 1981 traditional work showed them reaching column densities of something like 1,000 grams per centimeter squared. Recent work by Padavani has suggested they go to even higher densities. And so this is potentially a huge, important source of ionization at the midplane. So if we add in those cosmic rays, we get increased ionization by maybe 1 to 2 orders of magnitude within 10 AU or so. So now if we have the ionization rates, we can carry out chemistry through post-processing and figure out what the dominant ions are at all points in the disk and how the ionization changes as a function of scale height. Now, these are not full MRI calculations, but knowing the ionization rate, the ion abundances, we can go ahead and calculate through 2 dimensionless parameters that dictate the onset of the MRI. So we have the ambipolar diffusion number, which basically tells you how coupled ions and neutrals should be, and the magnetic Reynolds number, which tells you how well the plasma is coupled to the magnetic field, right? And so various work has suggested the MRI is active when this ambipolar diffusion number is greater than 0.1, Reynolds number is greater than 3,000. So you can put this together and determine where the MRI active region actually is. And so in this particular fiducial run, you see it's not active at the midplane. So it's not creating a huge amount of turbulence, which seems to be consistent with observations, and it doesn't seem to be interfering with the formation of planets in this particular case. So that's encouraging. But there's a lot that we don't know about cosmic rays, right? And the propagation also depends upon things like the size of the dust. So the larger the dust grains, right, the more ionized the disk becomes. So that suggests that this problem gets worse in time if you're trying to form planets. And it also depends upon the propagation, which we unfortunately don't know very well. And so if you assume that the propagation is diffusive, goes as 1 over r, then you're beginning to get ionization down at the midplane when it interferes with planets. All right. So that brings me to my conclusions. Right? So based upon this work, we think that low energy cosmic rays are accelerated locally within star-forming regions from shocks and jets. And these can play a significant role in the surrounding gas, in the cores and disks where they are irradiating. And this does seem to have an effect on disk ionization and will impact the dynamics and evolution of the disk, particularly in the inner disk, where they're able to reach distances very close to the midplane and increase the ionization. Thank you. Yes. I don't know that off the top of my head. There's short-lived ones and long-lived ones. They produce different ionization rates. Yeah, I don't remember which ones that Ilse included in her work, but yeah. Mm-hmm.
So these are typically quite high ionization rates compared to, say, what you would expect in the field. But there are environments where this is effectively a diffuse background, like in the galactic center. So if you were to put these types of disks in a galactic center environment, do you expect that you end up competing or maybe even amplifying the cosmic ray rate that is sort of generated internally? Or is it drowned out against the background and basically everything starts behaving this way?
So the first thing I guess you can ask is what happens when you put clouds in those environments? And it definitely raises the cloud temperature to, say, 30 to even 50 Kelvin if you're enhanced by cosmic ray ionization rate. But again, in these disks, as long as you have this magnetosphere, it can really screen out a lot of the cosmic rays. I don't know about the high energy ones and how those interact, but even if you raise it by 2 orders of magnitude, I think that magnetosphere is probably going to do a lot in terms of keeping out the ones from the local environment.
So Stella, somewhere along the talk you mentioned that you don't want the MRI to go to the midplane because then it becomes too turbulent, you can't make planets.
Yes.
So I didn't get the bottom line from your model with these parameters. Does it penetrate down to the midplane, or do you still have a nice quiet zone in the middle of your disk?
It depends upon your parameters and assumptions. So it depends partially on the cosmic ray diffusion and how they diffuse. If they diffuse as 1 over r, then yes, there will be a lot less places within the disk that are quiescent for planet formation. If it doesn't look like they're reaching the midplane. So one of the reasons why I was doing this project was to see if we could rule out this model, right? So we have observational constraints on MRI turbulence in protoplanetary disks, and if this doesn't agree with that, then we need to go back and reevaluate this whole idea. But I was not able to rule it out. So it does seem pretty likely the cosmic rays are there, are not. They're facilitating the MRI in some cases, but they're not completely blowing up the disk. Yes.
Okay.
Yeah.
Sound okay? Whoops. Okay. Thank you, Charles. So as Charles says, hey everyone, my name's Theron Carmichael. I'm a 5th year graduate student here, working with Dave Latham on my thesis project that is focused on the detection and characterization of transiting brown dwarfs. So for this talk, I wanted to sort of outline the process that we typically follow to find these types of objects, and save a little time for discussing how doing so helps us address the question of brown dwarf formation. So let's first think about these 3 different types of objects here. So there are gas giants, brown dwarfs, and low mass stars. And so as I've sort of pointed out here, as it happens, these 3 different types of objects can all be about the same size, as in they can all have a radius that is about 1 to 2 Jupiter radii. So from that metric alone, that makes them somewhat difficult to distinguish from each other. But fortunately, of course, their masses are very different. So gas giant planets typically range from 1 to 13 Jupiter masses. Brown dwarfs are somewhat arbitrarily defined to be 13 to 80 Jupiter masses, and then you have low mass stars at anything above 80 Jupiter masses. Now, this threshold in particular is chosen. The 80 Jupiter mass is chosen because that is the threshold at which you can fuse hydrogen in the core of the objects. But the lower end here, 13 Jupiter masses, that is a little bit that is more arbitrary in the sense that really depending on metallicity, that's the mass at which you can maybe fuse deuterium in the core of the object. So it's a little bit hazy exactly why that's chosen. So the way I want to think of this is then let's maybe consider how these different objects form. So typically we believe gas giants are formed via core accretion in the disk in the protoplanetary phase, and for the most part, stars will form via some sort of gravitational collapse, right? And we're not sure at what mass range in between these two sort of planets and stars do these formation mechanisms switch or change. So maybe there's a thought of if something up to say 20 Jupiter mass is formed via core accretion, maybe you want to call it a planet instead, right? So that's sort of one of the driving questions behind why we're looking for more of these types of brown dwarfs. So how do we actually find them? And to remind everyone, this is how do we actually find brown dwarfs that orbit a star. So this is a very specific type of method here. So first step, you let NASA launch an approximately all-sky survey mission. That's the test mission. So Hannah mentioned that in her talk. It's mentioned several times. So Transient Exoplanet Survey Satellite, that will do something like this, where it will scan the southern and northern ecliptic skies. Each of these sectors that it's kind of flushing out here is 28 days. It looks at that as part of the sky for 28 days, and it will give us a map that looks something like this, where we have overlaid in the yellow the Kepler and K2 mission footprints, but the test footprint is all of this here. So we're getting most of the sky. It's been altered a little bit since the mission launch, but this is basically still true. So most of the stars that TESS will look at will have a 30-minute cadence, and as I said, most of them will have at least 28 days of observing time, which means TESS is very much primed to find these short period types of objects. So things that are, say, less than 10 days, so you get at least two transits per sector. So with that step out of the way, TESS will start producing a lot of these light curves, generating a lot of light curves, and we get a lot of reports that look something like this, where we kind of vet them and try to determine from those what is the approximate radius of the companion object. That's important because, like I mentioned, hot Jupiters, brown dwarfs, and low mass stars all have about the same radius, but you want to at least check first that you have the right radius. So in this case, a typical, say, 1 to 1.5 solar radius star hosting something that gives you a transit depth of, say, 0.5% up to like 0.7%, that translates to something that is about the size of Jupiter. So transits are important in this case for this reason. They give us the companion radius, and another important piece of information that we get is the orbital inclination. So that is the inclination of the plane of the orbit of the candidate object, and that's important for this next step in particular to get the mass of the planet, or mass of the object, the candidate object, I should say. So that manifests itself through taking what are called recon spectra. So essentially what you're doing here is you're taking a spectrum at a certain point along the radial velocity phase of the orbit here. So you want to start here and here, basically, to get a sense of how much of an amplitude, how much of a radial velocity amplitude that this candidate object has on its host star. And in the case, in this example, so something like a 4.5 kilometer per second pull actually translates directly to a brown dwarf. So you can now take this information, plus the information we got from the light curves, namely the inclination, and that lets you get a actual mass of the object. So now we're left with, after all this, a mass and a radius of a brand newly discovered brown dwarf. So I'll go over in the next few slides a couple examples that we have discovered using tests and this sort of follow-up method with ground-based spectrographs. So this example is the one I just showed. It's TOY 503. It's intermediate mass brown dwarf, 53 Jupiter masses. It's in a circular orbit, orbiting an A star, and in 3.7 days. I'll just note that this one is a little bit challenging in the fact that this transit was rather shallow, making it more difficult to get a precise measurement of the radius, but nonetheless, we still are able to extract the radius, which is, I think, the main takeaway, important point here. Another example that we're still working on right now is TOI 629. This is another sort of intermediate mass brown dwarf, a little bit more massive than the previous one, also orbiting an A star in a longer period, and this is still eccentric. So maybe, this is I'm mostly showing this to give everyone a flavor of the different types of brown dwarfs that we have found so far using the test mission. Okay, so now that we know how to find them, let's look at where all these brown dwarfs sort of lie in the context of low mass stars and giant planets. So this diagram is showing in log scale the mass on the y-axis in units of Jupiter masses, and then the period in days. And I want to emphasize with this plot, this sort of magenta band in the middle, that is, as far as I can tell, like complete, as in like I haven't missed anything being plotted there, as far as what objects have been published and a couple unpublished ones. So whereas the giant planets here and the low mass stars, I'm sure I'm missing several or more points there, but this is really to derive from the point that we seem to be missing a lot of brown dwarfs, where we know they're more massive than the giant planets, so they should be easier to detect in radial velocity surveys, yet we're not seeing them. So that's one of the big questions behind my thesis, and that we're trying to address, maybe not answer fully, but address and find more of them. So let's look at just the population of brown dwarfs now, and I want to point out here, the points in the stars are the ones that I've had a part in contributing to characterizing from the test mission in particular. So we've had, I'll say 4 new brown dwarfs and 1 star. It's right on this sort of 80 Jupiter mass threshold here. But the point of showing this is that, there are 23 objects here. That's not really enough to make a, claim about the behavior of the population or really point out any significant features in the mass distribution. So really, this is further motivation to find and detect more of these using the method I've described so far. So the last point I want to leave everyone with is the mass radius diagram. So we've worked hard to find the mass and the radius. The axes here are in Jupiter units once again. So this is sort of just spanning the brown dwarf mass range, and then we're not going quite down to 0 here, but just roughly around the size of Jupiter on the y-axis there. And so the idea with this is to take a look at the substellar evolutionary models here in white and see how well they actually predict mass, radius, and age for different brown dwarfs. You would like to have as many as you can brown dwarfs that are in, say, a star cluster, so you have a better handle on what the actual age is. In this case, there are only 3 such examples of brown dwarfs that fall into that category. Other than that, you maybe rely on astroseismology or things like that, but so far no host star has had good astroseismological measurements to get its age that way. And lastly, the other thing I'd like to try to address with my work is, as best we can, maybe reducing the error bars on some of these objects. This one, for example, is one I showed earlier where I mentioned the transit is shallow, so that's about the best you're going to get anyway. But for things like this, we might have an opportunity to improve as TESS scans the rest of the sky and might observe that one. It's a little bit faint, but maybe. So I'll leave my summaries up and just emphasize a couple of other points here. Brown dwarfs should be easier to find, at least certainly easier to find than hot Jupiters. We've found 5 new ones with the test mission so far, and more are coming along. I think by the end of the primary mission, so that's the end of summer 2020, we should have at least maybe 10 to 15 additional ones than from when we started before the test mission. And all this is sort of aimed at the goal of addressing the question of how brown dwarfs form and seeing if we can maybe rethink that lower limit dividing planets and brown dwarfs. So thank you. Right, so that's an interesting question. I mean, one thought I've seen out there is that the orbits of these brown dwarfs for some reason isn't stable, and so you're not finding them, but I'm not sure I believe that one as much. But as far as like the population being set, I think the way you have to think of it is, so you're kind of seeing the sort of two tail ends of two types of distributions of like formation, right? There's core accretion versus the way stars form. And at least my intuition right now, not having many brown dwarf discoveries yet, is that that's sort of the tail end of those distributions, and you're just seeing that deficit based out of that. Should that be uniform? I'm not sure. A lot of this right now is like sort of exploring and trying to figure out, to find more of them, to see if trends emerge out of that. So, yeah.
Here's a follow-up. So these are all transiting brown dwarfs and objects. So how does this compare to the field exoplanets, stuff like the field brown dwarfs?
So in terms of like how many there are, or?
Maybe in terms of mass function.
Right. So I'm less familiar with how people actually derive masses for field brown dwarfs. I can say there's a few thousand field brown dwarfs now, as in like not transiting anything. There's one known brown dwarf binary, which is interesting. So it's two brown dwarfs, right? But yeah, I admit I'm not as familiar with how masses are derived from a field brown dwarf. So yeah.
What is the metallicity distribution like of these brown dwarfs? Particularly, like, what do the models suggest happens when you vary metallicity? Because you should know isotopes, but...
So you mean of the brown dwarfs or their host stars?
Well, I'm presuming that they're both the same metallicity.
Ooh, okay. Sorry. The metallicity distribution, so of 23 objects, I mean, it ranges so that I can give you the limits, right? So the highest host star metallicity that we've found is actually this one right here. So this is a metallic lined A star. So it's 0.6 in FE over H. The lowest I've seen is like minus 0.2, I think. So that's the range, at least, that we've discovered. But again, I don't know if there's a really clear distribution of any sort here at the moment, but yeah. So essentially what you'd get is, for like a single age here, solar metallicity, so I guess I'm not plotting here, but metallicity will marginally affect the radius, essentially, as it gets older or more massive. But at these like ages like, say, 1 to 10 gigayears, so it's not a huge effect on the radius. So, but yeah. Everyone had a question. Next to you. Yeah.
I was just curious if there's any obvious explanation for why the blue stars have below 6 and 55. You have a poor determination of the radius and a good determination of the mass, whereas for 65 and 80, it's the reverse.
So you're talking about like this versus this, maybe. Yeah. So this radius is purely a result of the fact that the brown dwarfs, the transit was very shallow, so it's degenerate with the impact parameter and the radius of the object. So you can move it up higher and make it puffier, or move it lower along the line of sight and make it smaller. That's where that uncertainty for this object comes from. These other transits are not grazing, so we have a very good, precise determination of the radius based off that. That's purely that reason. And that is the case for like several other of these. This one, I'm not sure. This is just a faint star from Corot, and it just happens to be one of the worst, but yeah. Yeah, thanks.